Okay, so far we have seen the hardware solutions to solve the problem of synchronization. The first was the low level primitive, which was test and set and compare and swap like instructions, and then we looked at an abstract data types, which you will find in most of the programming languages, which goes by the name of semaphore. So as you saw, semaphores, it can take any values. It can take any values from essentially you can say more than one also. So it can be 10, 20, 30 based on how many processes or threads do you want in the critical section at one time. There is also one more term that you might come across, that is called mutex, and the full form of course is mutual exclusion. Mutex is a special kind of semaphore where you restrict its values to 0 and 1, that's all. So it's a binary semaphore, which is so you see, as an example, in our particular case of producer consumer problem, we actually don't need a semaphore. A mutex will be sufficient, but then the point is semaphore is a generalization, so you can say that it can cover a more wide variety of problems as compared to mutex, but in some cases you might find mutex more comfortable. So with mutex also you will find the similar instructions. The only thing is that it can only take the value zeros and ones, it can not go beyond 1. Before we finally wrap our discussions on semaphores and mutex, we will actually be looking at some more interesting synchronization problems. We have not completely solved the producer consumer problem, we are yet to code its solution. That I will be doing in Python in yet other video and will be sharing it with you soon. But before that, there is one more important thing that we should discuss about semaphore. So whenever we were discussing our synchronization solutions, we said that there should be 3 objectives that should be accomplished. The first one is of course mutual exclusion, that means only one process should be in the critical section at the same time. That, as you can see in this particular solution, this semaphore is guaranteeing us, right? That is one of the basic requirements that must be met, that is at one time only one producer or consumer should be in its critical section or should be changing the value of count at a given time. There are few other things, as you would have noticed in the lab document. Another important requirement is that of progress. Progress is something simple again. Progress means that you see, it's again taking the example of Ram and Shyam. If Shyam wants to meet professor and then Ram is currently not meeting, then Shyam should be allowed to meet him. Basically, you should not unnecessarily make anyone wait. And if you remember our first software solution which was given in the lab, that had a problem of progress. The solution which had like strict alternation, Ram and Shyam were altering in that particular problem. You see, they give turns to each other, they take turns. So the problem is that until and unless Ram goes, Shyam's turn will not come. That problem is also resolved here with semaphores with the help of these wait and signal operations. Right, so you should take a good look at it. Basically the point is, as and when producer comes out of its critical section, it changes the value of semaphore back to 1 and then consumer can use it. So under no circumstances you will find an unnecessary wait from the side of producer or consumer. And then there is one more thing that we should guarantee, that goes by the name of bounded wait. And again, that idea is, let's say one producer or consumer has a higher priority, then it should not be the case that every time producer just keeps on entering the critical section while consumer never gets a chance to do so. So again, our solution of strict alternation guaranteed that they will take turns, so that it couldn't happen in that situation. Basically, they could they go one by one, so there is fairness. But in this particular solution, you see, if producer, let's say, has a higher priority and is executing very frequently, then there is no count on how many times the producer is going in its critical section. Basically, it can keep on calling semaphore wait, count plus plus, then semaphore signal, and then again to wait, count plus plus signal, wait, count plus plus signal. There is no way that you can stop. Right, producer from entering in its critical section. No matter consumer is also expressing its willingness that it also wants to go to the critical section, but it is not being allowed. So in a single sentence, starvation is possible here. So we also need a solution to that. There is one more problem if we go by this particular definition of a semaphore, which some of you have already expressed your concern with during our lab sessions, is this infinite while loop. You see, infinite while loop adds a lot of unproductivity to your code. Basically, when your CPU goes into an infinite while loop, it is still executing a process, but then the point is it is just going round and round in circles. It's not doing any productive work. So it is same as if Ram wants to meet the professor, he has to go on and keep on checking back again and again whether Shyam is back or not. Right, so we need a solution to that. So in reality, your actual definitions of wait and signal differ slightly, and that you find it here. So it is it's a more realistic representation of your semaphore's wait and signal. So you see here again, being an abstract data type, just like how you define struct stack, struct queue, struct semaphore has been defined and it has a few variables here. So one is the value of the semaphore at any given time. What you also do is you associate a queue with this semaphore. So whenever you have an idea of queue, it is first in first out, and first in first out is always done so that the entire thing becomes fair, right? That's why you make queues outside any shop, so that the idea of fairness is guaranteed, and that is what is done here. So the definition slightly change here. Whenever you call a wait on semaphore, first of all you decrease the semaphore's value, and if you see that the value has become less than 0, so basically the idea is you cannot go into the critical section if this value becomes negative. So what is done, instead of putting you in an infinite while loop and asking you to check back again and again, this semaphore, it pushes this process to a particular queue. And you see, since it is the idea of queue, the one who wanted to go into the critical section first is at the beginning of the queue and will get access to the semaphore first. So with this idea, you are granting fairness along with your idea of semaphores. In addition, what you are also doing is taking away that busy wait or that spin lock, which was adding a lot of unproductivity. Now you don't put a while loop asking the process to check back whether the semaphore is free or not. What you do is you have a system call here and you make that process sleep, and the idea is you go to sleep, and whenever the critical section will be free, you will be signaled. Right? That is a more realistic approach. So instead of asking Ram to wait and check the professor's cabin again and again, if he comes and finds the professor to be busy, he can just go back and sleep in his room, and then again it is taken care of that the people know that Ram was here and he is waiting. So whenever one comes out of the room, they wake up Ram. So whenever signal means there is one process who came out of the critical section, when that happens, the value is increased by 1. And then if there is space inside, then you remove a process from the queue and wake it up. And you always remove that process from the queue which came first. So this grants a faster code. You see, that's why our code didn't take a lot of time. If you really implement the same code with a while one loop, it will take a lot of time. So it also makes your process more efficient, and it also guarantees you fairness. So this is the actual implementation of semaphore. Actual means more realistic. Actual implementation these days might differ more. So that was about semaphores. And then if you want to work with mutex, that is all the more easy and interesting. So you can use this library and this code here. The idea is that again this mutex is similar to semaphores, but then the idea of count is not here. You can just lock and unlock with mutex. Right, so you can, whenever a process goes into the critical section, it can lock it with the help of mutex, and whenever it comes out of the critical section, it can unlock it. So that is what happens with mutex. Now can you try that the same code that we have implemented here with the help of semaphores, given all the details to you in this handout, right? How do you, which library do you need for mutex? how do you initialize a mutex, all instructions are given to you, how do you lock a mutex and how do you unlock a mutex. Given all this, can you try rewriting the same code with mutex instead of semaphores? So I will appreciate if you do that. If you have any questions, please put them in the comments, and also if you have tried this on your own and you have come up with a solution with mutex, please put a link to your solution in the comment box. So anyone who comments regarding a question, regarding a solution, regarding to an observation, we always encourage that. So the more you interact, please note that I am always noticing, and we'll give you some brownie points for trying to interact and for trying to do new things and for your new observations. So with that, we have mostly got over with this idea of synchronization. But yes, what we will try next is, so we have all the tools with us, we understand how to use a semaphore, how to use a mutex. What we haven't yet done is, if you look at this producer consumer problem here, it is not yet complete. Although we got the race condition resolved here with count plus plus, count minus minus, but as some of you raised questions during the lab sessions, the code is still not very real worldly, in the sense that we were having the idea of a buffer there, right? Whenever producer was producing an item, it was putting it in the buffer and then it was increasing the value of count. Similarly, consumer was consuming an item from the buffer and decreasing the value of count. So you actually don't see a buffer here. Also, some of you notice negative values for count. That should typically not happen, right? Count tells you how many items are there in the buffer and you shouldn't allow that number to be negative. So we will try to write one more code. I'll probably have one more video coming up in the next few days, and I'll totally try to code from scratch the producer consumer problem exactly in Python. So we have already seen how do you use semaphores and mutex in C. They are pretty much use the same in Python. The libraries and the syntax might differ a bit here and there. So we will do the same thing in Python in our next video, which will probably reach you sometimes in next few days. So with that, whatever we had to do in the class was over, and happy Dussehra to all of you. I hope you watch these videos before Dussehra so that the wish matters. Otherwise also it is fine, and after you come back we will probably have a quiz on all these. I'll also give you a handout with some practice problems that you can try at your own end, right? So with that we will wind up. So one more video coming your way soon.